So at this point, we've talked quite a bit about Faraday's law and the idea that you can have a coil that has some kind of changing magnetic flux through its face. And when that happens, you get an induced EMF that motivates current to flow. Induced EMFs generate electric fields. I mean, that's what they do. That when we first started talking about them back with batteries, we talked about that. And so we need to talk a little bit about this electric field that's being generated. And to do that, I want to sort of harken back to, our first discussions of electric fields and try to make some sense out of what you know and how it applies to the situation that you're looking at now. So if you think back to the beginning of the semester when you first started talking about electric fields and electric potentials, we were looking at static charge and static charge generating electric fields. And it turns out that static charge produces forces that are conservative, which means that they have potential energy functions associated with them. And you can generate from a potential energy function an electrical potential function. And so we built this whole theory around the relationship between, an electric field, electric potential, absolute electric potentials at various points in the field, and the relationship between the distance between the points, what the electric potentials are, and what the electric field is doing. And that relationship ended up looking something like this. So delta V between 2 points equaled minus the integral of E dot dr, or if the field and everything was constant, just E dot d was equal to minus delta V. Okay. And you got pretty comfortable with that relationship. It related voltages. The whole idea there was that if you had an electric field, you were going to have potential differences in the field. If you created a potential difference, like for instance with a battery terminals, that would create an electric field, which you could use to motivate charge to flow through a circuit. Okay. And as I said, this all had to do with static charge. We never did this, but we could have related the EMF of a battery to the electric field that it generated in a circuit. It turns out that EMFs are related to their electric fields by the integral of E dot dl. So we could have started right at this positive terminal, and we could have taken E dot dl all the way around, which would have ended up equaling our EMF. And we could have related that to the voltage difference that's generated by these two plates on which there's static charge. And if we went from here to here, the voltage difference would have been V final minus V initial, which would be the final terminal would have been negative, the initial would have been positive, and so the delta V between there and there would have been inherently negative. Okay, which means, given the fact that EMFs have to be positive, they are positive generally, apparently the EMF was going to end up equaling minus this delta V quantity that we generated by going from here to here as we were doing this E dot dl integral. Okay, what that meant was that the EMF, which equals E dot dl, equaled minus delta V, and lo and behold, there is this relationship that you would come to know and love back when we were talking about static charge. And that's not surprising because you're looking at static charge on these plates. Okay, we didn't do any of that, but we could have. Now, here's the rub. You have a magnetic field, and you have a coil sitting in the magnetic field. And according to Faraday's law, if you change anything, the size of the coil, you rotate the coil, you increase or decrease the magnetic field, if in some way, shape, or form you change the magnetic flux through that face, you're going to end up producing an EMF. It would be nice to link up what we know about EMFs with the relationship that we just got done deriving as we were talking about EMFs having to do with the static charge situation. But the problem with this is that if you started here and figured out what the circulation of E was, so if you had a little dr and you took E and you did E dot dr all the way around the closed path, you would get a non-zero number. But delta V between here and here would be zero, which means you have the situation that it looks like it doesn't make any sense, even though you're using a relationship that you've already kind of convinced yourself is a good relationship. Now, it turns out there's a perfectly good and reasonable explanation for why things aren't working out here. And the explanation is that the electric field, or the forces that are involved when you have an EMF set up in this kind of context, where it's being generated by a changing magnetic flux, it turns out that those forces are not conservative. And because they're not conservative, you can't define a potential energy function for them. And as a consequence of that, you can't define an electric potential function for it. Which means this relationship is nonsense when it comes to this particular kind of circumstance. It is still true, though, that the EMF that is being generated is going to end up equaling E dot dr from where you start to where you end. So what we can do is we can note that the EMF we've already figured out, according to Faraday's law, is minus n times the rate at which the magnetic flux changes with time. And if we link that up with our E dot dl and have the integral go around a closed path, which is to say our loop, or our circuit, we will end up with this relationship that effectively says that the integral of the electric field dotted into dl will equal minus the change in the magnetic flux with time through the face of the coil. Now, there are a couple of things, and I've kind of jumped the gun here, so you're sort of seeing them, but there are a couple of things that need to be noted about this. The first is that this integral right here is a line integral, and it's basically determining the circulation of E around dl. And you've run into a circulation kind of situation when you're dealing with Ampere's law, okay, B dot dl. In any case, that's what this is. So you're really looking at the circulation of E around that path being related to the rate at which the magnetic flux is changing with the negative sign out in front. So that's the first bit of amusement. The second bit of amusement has to do with the direction of dl, because if you take a look at this situation here, okay, dl could go this way. I say at this point, it could go this way or it could go this way. But you have another vector that needs to be defined in this mess, and that is the vector A, because the magnetic flux is equal to B dotted into A. And A has got to be perpendicular to the face of the coil, which means in this case it either has to be into the page or out of the page. It turns out that once you've defined your direction of A, dl has to be in a particular direction by definition. And effectively what that definition is once you've identified the direction of A, you take the thumb of your right hand and you put it in that direction, and the direction that the fingers of your right hand curl in will give you the sense of the direction of dl. So in this particular case, in this particular example, if A goes into the page, if you take the thumb of your right hand and you orient it into the page, and you look to see the direction that your fingers will curl, you will notice that they will curl clockwise. which means when you define this vector, when you decide to do this E dot dl operation, dl has got to be clockwise. So the point here is, once you've defined A, dl is sort of de facto defined, and you simply have to know how to do that, and I just explained how to do that. If it isn't clear, go back and take a look at the slides, because it's all explained in the slides. So let's take a look at an example. So you want to derive the expression for the electric field, assuming that the magnetic field in this case is increasing. If you use Lenz's law, you've got a magnetic field into the page, the magnetic flux is increasing, which means the induced magnetic field has got to come out of the page. And if you use the right thumb approach, that's going to end up suggesting that the current is going to have to end up being counterclockwise, which means the electric field is going to be counterclockwise. So that's the first bit of information that's important to note. Okay. How about the direction of dl? Well, I usually put A to be in the same direction as the external magnetic field, which is into the page. So if I put my thumb into the page and let my fingers curl, they will end up my right hand, they will end up curling in a clockwise direction. So E is counterclockwise. The DLs are going to end up being in a clockwise direction. So if you take all that information, there's my little DL for this particular point, there's my E for this particular point. You take all that direction, the external magnetic field into the page, because you're going to have to take the change in flux with time, so you need to know what B dot A is, and the B is the external magnetic field. The external magnetic field is into the page, A is into the page, so the angle between the two is going to be 0. And the electric field and DL are at 180 degrees with one another. So when you do the math, this quantity, B times A is pi r squared because it's a circle, and the angle between the two is 0 because they're both into the page. And for this, E, it's going to be constant, same magnitude everywhere around the circuit, so I'm going to pull it out of the integral. I'm going to have dl, and then the angle between those two is going to be 180 degrees. You can just see it looking there. So this is going to give you a negative sign, and you fuss with the math. The only thing that's changing here is B. By the time you get done, you get this expression that says E is equal to R over 2 times the rate at which B changes with time. Okay, so having done all of that, you kind of see how the math works. Let's assume that you have a magnetic field that changes at a constant rate of 2 over pi r squared. So what's the induced EMF in this case? So I go ahead and I figure out, I just do the math. Okay, I know what B is, so I can put B in, or excuse me, I know what dB/dt is because I know what the magnetic field is changing at this rate. So this is dB/dt right here. So I go ahead and do all the math, come down to pi r squared times dB/dt. And by the time I get done, I get this answer of the EMF is equal to -2. And the question arises, what is that negative sign telling you? Now, it turns out that I've basically just kind of raked you over the coals. I've given you a whole lot of information. And it turns out that the second part of your assignment, if you look at, the assignment that you've been given for today, is to go ahead and read through, I think it's slides 43 through 47 or something like that of the PowerPoints, of the class PowerPoints. And they will explain to you what's going on with that negative sign. And you need to read that. I'm not going to go ahead and go through it here and now because it would take quite a while and it's kind of convoluted. And it's the sort of thing where you just kind of have to sit and just sort of think and just kind of meander through it. And I'm just going to let you do that on your own. But in any case, at least now you know how to figure out what an expression is for the electric field in a situation in which you have an induced EMF generated by a changing magnetic flux through a coil. And that was basically what this screencast was attempting to do. So that's it.